What's up, Ollie? What's up, Ghost Rider? Pretty sure, actually. Bet. How long is the video? 50 minutes. What the fuck? Love what you've done with your hair. Thanks, bro. I'm about to cut it all off, dude. It's getting really annoying. Make sure we get that homework done. Maverick Burger. I'm gonna talk to you in a while. I'm early as fuck. Hey Aiden, how are you? I'm good. Alright. Should I just get this out of the way? Bro, I'm gonna cut it all off. It's getting annoying. Oh, that's a piercing thing. Yeah, 2 homework assignments due tomorrow. It's fucking bullshit. Wait, which one should I do first? I'll do gas laws today. I'll do some of it. I'm gonna do most of it tomorrow, but I'll maybe look at some of it today. Look, you're my favorite streamer right now. Thank you, bro. I use this extension right here. They put my chemistry class on here? Fire. Oh, here's all my exams. Oh, we have retakes? We have retakes? Oh, shit. What's that noise? $5:30 to 7:30 p.m., dude. What are you talking about? Do we have a syllabus, bro? Okay, apparently this is all on Atlas. I don't know what Atlas is, though. Okay, this is fucking stupid. What is this? Bro, what is going on? Bro, can we see a syllabus, bro? Oh, I need to pay for, this. What's up with all these apps using two-factor authentication, bro? Oh, what the fuck? There we go. Just paid for that shit. What are you talking about, Atlas, bro? I'm so confused. Bro, she didn't paste the link to the class. It's just like the Atlas homepage. Alright, whatever. So no syllabus, dude. Posted yesterday. Okay. Oh, she emailed us? She did not email me. Well, yeah, I haven't received any emails from her. Yeah, no, dude. She had not emailed me. Okay, well, I need to get these emails. So I need to email Kelly Morville. Oh wait, I think I copied her email. Yeah, I did. Alright. Yo, I'm taking discrete maths next semester. Any thoughts that what worked for you? Just study really hard. Physics or computer science? I'm both. Are you using GNOME? Yes. Yeah, YouTube's pretty good. For my course, like a lot of the YouTube videos strayed away from how I was taught things, like, and how they wanted me to do things at my university, but YouTube videos are pretty good for concepts and stuff. You got a streaming schedule? I don't know. My ex is going to UIUC. That's sick. What's up, Robert? How you been, bro? What semester are you? I just got finished with my second semester. Alright. I'm gonna eat really quickly. So, I'm muting. What's up, Zach? See. Let's get this shit over with so I can get up out of here.
Lecture in our last lecture in thermodynamics, and this is going to focus on what's called the Carnot cycle, and it was a process developed by a French engineer named Carnot.
Wait, this cycle first. Oh, I didn't do the thing. Hold on. What the fuck is this? Yeah, I'll come in a second. Hold on. constant temperature. Huh, constant temperature.
No. And in this process, he was...
Read this.
He was able to figure out a way to operate any thermodynamic device, a heat engine, a refrigerator, air conditioner, heat pump, at maximum efficiency. So that's what we're going to be looking at. I know I need my heat engine so I can drive to work. How can I get the greatest peak performance out of that engine? So we're going to start off with focusing mostly at engines on it. Now, if you read the majority of physics books out there, they talk about a Carnot cycle starting at a high pressure, low volume state for that gas. And the first thing we're going to do is undergo an isothermal expansion. Now remember, isothermal means we are at constant temperature. So we're going to have heat blow into this part. Then we're going to undergo an adiabatic expansion. No heat is flowing, but it's a very rapid expansion. And then as we've expanded this thing as far as we can, we're going to have to go back to where we started so we could make it a cycle.
Because PV equals nRT. And N and R constants. Wait, but how can we have isothermal expansion? Wait, go back, what?
Thing we're going to do is undergo an isothermal expansion. Now remember, isothermal means we are at constant temperature.
So why does heat?
So we're going to have heat blow into this part. Then we're going to undergo an adiabatic expansion. No heat is flowing, but it's a very rapid expansion. And then as we've expanded this thing as far as we can, we're going to have to go back to where we started so we could make it a cycle. Why would we use a cycle? Well, we can't just expand and keep expanding forever. That would take an infinite amount of energy and space. We've got to have our engine be portable and compact. So we're going to undergo an isothermal compression, and that's going to release QC, this waste heat. And then we're going to go an adiabatic compression up to this point. So the total work is going to be the area enclosed by this. We can't make that really a geometrical shape that we could calculate. It would take calculus to do these kind of things here. So we're still going to study it, even though we're not going to actually find that area. Let's go ahead and turn your page. And we're going to talk about how each part of this cycle is going to give us maximum efficiency.
Okay. Let's see. Yeah, because it expands. When you add heat, it expands, so it creates outward work. And when you lose heat, then it compresses, meaning work is done by the outside on the system. Yeah, makes sense. Adiabatic expansion. What the fuck does adiabatic mean? We have that shit. Adiabatic. Everything changes. Net heat is 0. So heat does not change. So delta U equals W. So that means all the internal energy is converted into work. So heat is net heat change is 0. And net heat is 0. Okay. So heat in adiabatic expansion, the heat delta Q is 0. Yeah. Delta U equals Q minus W. Q equals 0. Delta U equals 0. So we get delta U equals W. Oh, negative W. Cooling? What is he talking about cooling? Done by the gas. Oh, this is expansion? Yeah. That makes sense. Okay, isothermal compression. Probably gonna get delta U equals 0 again. So Q equals W, but this time Q is gonna be negative, right? Yeah. Which means, let's try to think about what this means. 100% of heat loss is going to turn into work done on the gas. Is that what it says? Is used to remove waste heat. Work is done to cause heat loss. Adiabatic compression. Delta U equals Q minus W. And this time Q is 0 again. So delta U equals W. Delta U is going to be greater than 0. So negative W. So W is going to be less than 0. And this means that 100% of work done on gas
So in our first part, we said an isothermal expansion. Isothermal means constant temperature. And if our temperature does not change, delta U is 0. So Q is equal to W. So that means all of the heat we add forces the gas to do work, or 100% of this heat that we absorb creates work done by gas. And that sounds fabulous, all right? If I could take 100% of the food I eat and make it into useful energy with no waste, life would be a lot easier, but it's not going to be that clean. Next one we go through is an adiabatic expansion. And that adiabatic means Q is equal to 0. We said that this was a very rapid process. So we have something very well insulated with very little time for heat to be moving. So during that process, we have work done by the gas. So if that work is positive and we have a negative here, that makes this negative. So if you can't see that negative in your notes, darken it. And if delta U is negative, that means our gas is losing internal energy. Or in magic marker physics, our gas is cooling off. But 100% of that loss of internal energy, that cooling, becomes useful work done by that gas. So we're still optimizing this thing's performance. Great. Now we've expanded as much as we can. We got to get back home to make it a cycle. So we're going to go through an isothermal compression, right? And again, that means delta U is 0. So we get Q equal W. But our work, because it's a compression, is a negative number. So this is input work. And all of that work done on the gas is used to remove heat. So that energy's got to come from somewhere. It might come from another piston in our car or truck that's expanding at that moment, all right? But we're taking all that energy that we're putting in and using it to get rid of the QC. Then we got to undergo what's called an adiabatic compression. And when something's adiabatic, that means no heat is flowing. Q is 0. Since we have a compression, our work is negative. So a negative makes this a positive. And 100% of the input work we do raises the temperature of the gas. Because I need that gas to be hot. So when I explode it, I get the right efficiency. So each of these processes has something about them that makes it ideal. However, trying to run this thing on this cycle is not practical at all. These isothermal processes we called quasi-static last lecture. And a quasi-static process means it occurs very slowly so that the system stays very close to thermal equilibrium. Right? So yes, I'm changing all my heat into work, but it's going to take a near infinite amount of time for that to happen. Well, I don't have an infinite amount of time. So processes 1 and 3 are not practical because with too much time, our power is going to go really, really down. So you might wonder, why is Mick talking about this? There's a reason behind everything. And I wondered that when I was taking this class, but I was in a class of 300, so I couldn't really ask that question. If these things could help us figure out the upper level of performance, and we build a heat engine and it runs maybe on the diesel cycle or the Otto cycle, and we get close to that percentage of performance, that could tell us we're doing a good job. So if Carnot said, hey, you're at 40% efficiency predicted, and we build a heat engine and it actually comes out 38% efficient, we did a really good job. So it gives us an upper limit to shoot for. So it's still important to understand, even if we don't run it on that cycle. let's go ahead and have you turn your page. And we're going to talk about how to try to change that into an efficiency. Remember, we said a heat engine is designed to absorb heat in.
Hold on. Okay, that makes a lot of sense. Thermal efficiency equals work over input heat equals change in heat over the input heat. And that's always going to be greater than, oh, it's always going to be less than 1. It's always going to be less than 1. So it creates work as an output. Yeah, because it's an engine. I was thinking of like a refrigerator or something. They take work in, inputted work, and then they output heat. Well, not a fridge, but like a heater. Okay. So we have our Carnot efficiency, it's something new, equals TH minus TC over TH. And that's obviously going to be less than 1. But it also equals 1 minus TC over TH. Yeah, that makes sense. And this must be in Kelvin. And this is the max possible. Okay. Upper bound,
into
bro.
the gas
Discrete math.
by having 2 different temperature reservoirs. Heat always wants to go from hot to cold. So as heat naturally enters the gas, it's going to force the gas to do work, and then we're going to dump that waste heat, QC, to the cold temperature reservoir. So this was our efficiency. Remember, it's more than just output over input. And the physics books say it that way. I don't like it that way. I like writing it as my goal divided by my input action. Both of these things are output, but that's my goal to focus on. So we learned that our work is the difference of those heats. So when we subtract these things here, that is the equation we saw last lecture. So again, this is going to be less than 100% efficient.
Ow!
So this is where the Carnot comes in. If we run it on the Carnot cycle, for the 2 isothermic processes, temperature is constant. So the heat from the hot reservoir is proportional to temperature of the hot. The heat from the cold reservoir is proportional to that temperature of the cold. So we're going to replace these Q's with these T's. And this gives me my Carnot efficiency, my peak efficiency, my maximum possible efficiency, my limit of efficiency. And when we look at this expression right here, units are going to matter. All of this must be done in units of Kelvin. The numerator will be the same whether it's Kelvin or Celsius, because it's a difference. But the denominator must be Kelvin. If I could put 0 in for the cold environment, I'd have a 100% efficient heat engine. If I were to go out today where it's well below 0 Celsius, I'd have a negative TC and I'm over 100%, but the math doesn't work that way. So in your notes, must be in Kelvin. Now we could take this and break it up, and you'll sometimes see this form of the equation. And that really helps us see here that the bigger the difference between these two, the smaller this fraction's going to be, the greater the efficiency we're going to have. So you got a salesman comes up and says, hey, I got your next heat engine here, and it's going to give me 100 joules of work for every 220 joules of heat absorbed while operating between those two temperatures. And we want to know, is his claim accurate?
Let's draw that word. So he's making a heat engine, so work comes out, heat goes in, and heat goes out as a byproduct. Yeah. So his claimed efficiency. So we say efficiency equals our goal over our heat, so work over QH. 100 joules of work for 100, so 100 over 220. 10 over 22. 5 over 11. 45%. Okay, and now I assume we want to find this Carnot efficiency, because that's going to give us what his efficiency actually could possibly be. Right? Is that what we want to find? Yeah. And we know Carnot efficiency equals that equation, TH minus TC over TH. Let's convert everything to Kelvin. So TH is going to be 120 plus 200. Fuck. It's like 200 something 0.15, 273 maybe? Oh, it is 273.15 plus 273.15. Okay, so we get our TH equals 393.15 Kelvin, and our TC equals, it's the same, it should just be the same thing, just minus 100. Yeah, it is 293.15 Kelvin. So that equals 100 over 393. So it's not going to be possible. We get 25%. So his efficiency is way too high.
Now, he's not saying you're going to get more than what you put out, right? Claimed efficiency of 100 over 220 is 45%. That's a really high number. That's like coal heating water to make electricity efficient, electric car efficiency. So he has my interest, because most cars, we said, are 10 to 20, 25% efficiency maybe. So what we're going to do is then take these temperatures, put them in the Carnot efficiency equation, and we only get 25% efficient. So there is no way this can be accurate. So if we take the 25% efficiency times the QH, we're only going to get out 55 joules, not 100 joules. So I know his claim cannot be accurate, and he needs to leave because I don't want to talk to him anymore. Now, if you put the numbers into here and you use Celsius, you'll get a different number. And even though the units drop out, the number is wrong. Because again, this has to be in units of Kelvin. It's got to be absolute. So this is the one part where I say we've really got to try to stick.
Yeah, well, you get 100 over 120.
Absolute temperatures.
Can we flip the page, chat?
Now let's take a look at a heat pump.
Silence, boy. Dude, how we have so much... How does he click? It says there's 30 minutes left of this lecture. Okay, wait. We're at 12:29. Somebody remember that. Okay, Google's gonna remember it. What? So he actually is gonna talk for 30 more minutes? Where are we at? 12:29. What is this bullshit, dude? Okay, heat pumps. Okay, what is a heat pump gonna do? So we're gonna get inputted the cold, output the hot, and we're gonna input work, right? This might all be wrong. Oh no, it is right. It's all right. Output heat, input heat, and input work. Yeah, that makes sense. Okay, for a refrigerator, it's essentially the same thing, right? Okay. In a heat pump, we input work. On the gas. To move heat. And we know this thermal COP. We have that equation, so it's QH over work equals QH over QH minus QC. The Carnot cycle states that QH is proportional to TH and QC is proportional to QC. Or to TC, fuck. Yeah. So we know the Carnot COP equals TH over W or TH over TH minus TC. Yeah, and that is always greater than 1. And this, remember, this has to be in Kelvin. T coils, what the hell are they talking about coils? Is less than T outdoors. Okay, he's getting into some fucking absorbs QC. Oh, I get what he's saying. Like the metal coils are colder than the outdoors, so then they absorb heat and then transfers that change in heat to the inside. T coils is greater than T indoors. Release heat.
Now let's take a look at the heat pump.
Okay, wait, let me write that for refrigerator first, actually. input work on the gas. Move QC from cold. No, let me not write it like that. To move QC to thermal COP is gonna equal the same shit, dude. Silent, boy. Oh, it's because he's playing with the cat. Be quiet. Carnot's COP is gonna equal TC over TH minus TC. So essentially just makes the coils colder than the fridge so that they absorb heat out of the fridge and then release them into the air outside. Wait, but how does it release it? It must release it by heating it up. So it takes the heat out of the, okay, so it makes itself colder than the fridge to take heat out of the fridge, and then it inputs work to heat up all that air or whatever gas it is. It heats it up, and then it gets rid of the heat by being hotter than the outside. Yeah, makes sense.
It's going to use an input of work on that gas to remove heat QC from the outdoors and deliver it. So its coefficient of performance is what is my goal. And this is where I want you to be self-centered and selfish. I and you are going to be inside, and we care about what is sent into our room to keep us warm. We're not worried about stealing heat from the outdoors and Mother Nature. This is what we need.
No, you're stealing
So
heat.
in order to get this, we have to input work. So my goal is my QH, and my input is my work. And this is the same equation we had before. So since my numerator is bigger than my denominator, this is going to be greater than 1. So we can't really call it an efficiency. If we run this on the Carnot cycle, we could then replace these heats with their absolute temperatures. And this would give us our Carnot COP. And again, it must be in Kelvin. Now, to make this happen, to steal the heat from outside, we need to make our coils colder than it is outside. And to send the heat inside, we need to make our coils hotter
Okay.
than the inside.
I kind of can like
to radiate that in.
I already understand this.
So the biggest track, we're
you
going
have to keep it's redundant.
And the hot state,
And I'm kind of in a rush.
I want you to read. We're going to have a heat pump that operates at
we have 4 pages left. Maybe I can just come back and do this later. Well, no, actually. Well, let me just hold on. Well, the more I think, the more time I'm wasting. Let me make one phone call. And then we can. Okay, well, no answer, so I'm gonna continue working. Okay, why do we want this? Why do we want to know that this is 23 degrees Fahrenheit? Yeah, I don't care. I'm actually erasing that. That's useless. I only care about SI unit conversions. I'm sorry. Okay, let's grab our equation sheet because it seems like we need it. So this R. Okay, wait. Can we look at this? Heat pump order. 40%. Okay. And the wall ceiling have an R value of 3 meters squared degrees Celsius per watt. Temperature inside of the house is 20 degrees Celsius, and the temperature is 5 degrees Celsius. So we have a delta T of 25 degrees Celsius. So our Carnot COP is going to be equal to, wait, it says Carnot COP, yeah, 40% of it's Carnot COP. So we have our Carnot COP being -5. Wait, can we have a negative in the numerator? I guess. And then we have 25 on the bottom. So we get -1/5 as our Carnot COP. Is that like I guess it's not an efficiency. Okay. -1/5, I guess. Okay, our R value, our R is gonna equal 5.68. What is this 3.0 times 5.68? Oh, because he's trying to get into different units. Yeah, no, I don't care about that. Okay. Oh, well, I guess I'm getting ahead of myself. I should probably read the question first. Okay, determine the amount of heat loss through the walls by conduction in 30 days. Okay, so we know conduction is delta Q over delta T equals area times TH minus TL over R. Yeah, so we have our R values, we have our delta T, so we need to find the area. The area is going to be 15 times 12, no, it's going to be 15 times 10, that's times 2, 15 times 10 times 2, so 300, then we're going to have 12 times 10, times 2, it's going to be 240, and then our ceiling is going to be 15 by 12, we only have one of those, so we get 300 plus 240 plus 180, so our area we get 720, 720 meters squared for our area. 25 degrees Celsius for our TH minus TL. And then our R value is going to be the walls and the ceiling. Okay, so we get 3 in the denominator. 3 meters squared degrees Celsius per watt. And that's going to equal watts in the numerator. Celsius meters are going to cancel. So we get 720 times 25 over 3. I get 6,000 watts, or 6,000 joules per second, is the heat loss. And that's the answer. And then find the cost to heat the home with resistance heating. The fuck is resistance heating? Resistance heating. Okay, so we know the time's going to be 24 times 30. We're at 6 kilowatts times 720 hours. So that's going to equal 4320 kilowatt hours. And we're at 10 cents per kilowatt hour. So we are 432 cents? $4.32. Oh no, we're at $432. Wait, what? I thought it was 432 cents. Because we're multiplying it by cents?
It's at 40% of its Carnot COP. So what does that mean in English? If my Carnot COP was 10, the actual COP is 40% of that, or 4. And we're going to have this house.
Oh, 0 point, because I'm
by 12.
No, it's not 10 cents.
Meters,
it's you're multiplying
and the R
it by
values
$0.10.
of the ceiling and the walls are 3.0.
Yeah, so it's $432.
The temperature inside the house is 68 Fahrenheit. Outside, -5°C, 23 Fahrenheit. Pretty close to what we're going to have today as I'm recording this lecture. Now, how good are these units? Well, if I go to Menards and I give them those units, they don't know what I'm talking about. So we're going to multiply by that nice number of 5.68, and these are my Menards or Lowe's or Home Depot contractor units. So we have an R of 17, which is a pretty good wall for the 80s and 90s. Modern code is even higher.
Can this nigga stop beating around the bush?
4,320.
Let's get to the...
Of that.
Oh wait, I skipped too far. But whatever, because I already did it. Shit's hella light. Okay, how much work must be done by the heat pump to maintain the temperature? Okay, so we have a heat pump. So we're gonna have TH, and then we're gonna have our TC. Let's think about how a heat pump works. So we're inputting work, right? We're also inputting cold heat and outputting hot heat with the input of work. Okay, yeah, right. How much work must be done by the heat pump to maintain the temperature inside of the house? Find the cost of operations at 10 cents per kilowatt hour. Okay, how much work must be done by the heat pump? So, do we know the efficiency? Oh, right, that's where this comes in. Because it was like, it works at 0.4% of its, it works at 0.4 of its Carnot efficiency. I don't understand how I got a negative number for my Carnot efficiency, bro. COP. Wait, why did I... Oh, because this is a heat pump, not a refrigerator. Such an idiot. Okay. This is it, and it has to be in Kelvin, so I don't know what I was doing anyways. 20 degrees C and -5 degrees C. Okay, it has to be in Kelvin anyways. 20 plus, what is it, 273.15, 290.15, 293.15. And then we have -5 plus that as well. So we have TH over TH minus TC. So let's do TH minus TC first. And then we can just take TH divided by that. So we get our Carnot COP equals 11.726. So our actual COP is going to be equal to 0.4 times that. So we get 4.6904. That's our actual COP. Actual COP, yeah, this is 4.7. Okay. So now, what does he want us to solve for? How much work? Okay, so we know that the actual COP is going to be equal to our QH over our work done. And we just solved for QH in the last question. Oh no, we didn't. We have Q, delta Q over delta T. Okay, wait, hold on.
Taylor? Hello?
Okay, I have a little bit of time here. So we need to find our QH. Interesting. Let me think about this. Okay, wait, there's a couple equations we can use here. We could also just say that our work... No, that's proportional though. It's not gonna be, like, you can't use subtraction. My Apple Watch is telling me to stand up. Okay, wait, let me think about this. Yeah, that's a fraction. Wait, do we have two unknowns? How is QH an unknown? It's not an unknown, right? Let me think about this. Wait, let me see. How is our QH our unknown? 4320. Wait, but how can we have it in watts? Wait, kilowatt hours. Kilowatt hours? Why would we want to have our QH in kilowatt hours? What's this guy talking about, bro? Okay, I guess we can do that. So we get 4.7 equals 4320 kilowatt hours. Wait, let me think about these units. Yeah, but that's a rate. They're really not, it's really not supposed to be a rate. It's supposed to be like an amount. Because our work is gonna end up being a rate then. So that means our work would equal 4320 divided by 4.7. Get 921.03 kilowatt hours. Like what? Yeah, he got 919, but that's because he didn't use the actual number. If I did 4320 divided by 4.7, yeah, he rounded. And I don't round, dude. I use the real numbers. Find the cost of operations at 10 cents per kilowatt hour. What is that? $92.10. Yeah. How could this system be made more efficient? Okay, I don't really know that answer to that question.
Let's see how we're going to do this now using a heat pump. So again, the whole idea of the heat pump is we're going to extract heat from the outdoors, stealing it from the bunnies and squirrels. And then we're going to move that heat inside by using work to send it indoors. So this is what we pay for. So our Carnot COP using absolute temperatures comes out to be 11.72. But again, that's the upper limit. We're not at that point. If we were waiting for it, we'd freeze to death because it takes an infinite amount of time. So what we're going to do is take 40% of that, and we get a value of 4.7. So that means for every 1 joule input, I get 4.7 QH joules output. So we're going to find the cost of the work. So we had in the previous question this as kilowatt hours, and that's still a great unit to use for heat, even though it's not SI, because electrical energy runs the heat pump.
Yeah, why
So
are we doing non-SI units?
Use that in kilowatt hours and divide by our COP, our work is 920 kilowatt hours.
All right, let's move on, buddy.
$91 a month. And that sounds great, but this is really just pushing numbers on a page. We wouldn't actually get this heat because we said this cold environment here was below 0 Celsius, below 32 Fahrenheit.
Oh wait, I shouldn't do the second
So
law
that
of
means we're
thermodynamics and
below
entropy
the freezing point of water. So
until
if we tried
later,
extracting this from the air,
because
frost would build up on all of these
I
coils.
think we're gonna go over that in lecture tomorrow, maybe.
So we would still freeze. So how do you fix that? You want to. So my in-laws that live in middle of Georgia, they need both heating and cooling, and they do get snow maybe every other year, and 1 inch of snow just ties up Atlanta, Georgia. They don't know how to drive in it consistently.
Dig it, that's stupid.
So they decided to go with heat pumps because they give them a great air conditioner.
I'm done. I'm done. So, I mean, I'll probably do work when I get back, but probably not gonna stream. Stream tomorrow. Wait, hold on. Okay, what is this? What are you guys saying? Okay. Hi Aiden, what's up Vaporeon? I was thinking you did a bachelor in physics and are doing a CS master's right now, but are you doing them at the same time? Yes, I am. What textbook does your school use? I calculated this COP incorrectly. I was doing it for refrigerators, but I was using a heat pump. Stupid mistake. So he's doing them at the same time. I am doing them at the same time. Some CS programs usually make students take some general engineering courses. Yeah, and that's where a lot of the like intersectionality between the majors is since CS is a Granger, like it's in the College of Engineering, a lot of the introductory courses count for both the bachelor's and the CS degree because they're the same. We have to take, well, CS technically doesn't have to take general chemistry, but everyone in Granger is supposed to take general chemistry. And then they have to take physics 211, 212, and then all the math is the same. Calc 1, Calc 2, Calc 3, linear algebra, statistics and probability, discrete math 1, discrete math 2. So all of those classes count for both. Are you in Kelvin? I also wasn't in Kelvin, so that was a problem. Besides mathematics, I didn't do anything. Yeah, that's maybe your school computer science was like in the school of science and not in the school of engineering. That's usually pretty common. When the CS program is not in the engineering department, they usually don't make you take a lot of these like physics and math courses. Yeah, my school, yeah, we essentially take the same thing that Richard Phillips says. A lot of math and a lot of physics and then a bunch of CS classes. You only had Calc 1, Lin Alg, probs, and statistics. Yeah, that seems okay, but I really think Calc 1 through 3 is pretty necessary. I mean, if you look at anything machine learning, you literally cannot do anything without Calc 3 because you need vector calculus. University of Central Florida, sick. Good luck to all with your studies. Thanks, brother. Hello, Karan. What's up, Dylan? I'm about to end the stream. I told you it was a really short stream. I mean, I think this has only been like an hour or two. But no, it's been only an hour. Maybe I should stop at 2 hours, so maybe I will finish this lecture. Oh wait, no, I'm not gonna stop. I have to leave. I mean, I told her I'd pick her up at 2:15, so I kind of have to leave. Does anyone know how credit is not given to both courses? Courses work. For example, I'm transferring with Math 213, and I'm wondering if I still have to take CS 173. Oh wait, you go to UIUC, don't you? Because I've seen a lot of these things, and I took CS 173. Credit is not given to both courses usually means that the courses are the exact same thing. So the school deems it redundant for you to take both of the courses, so they will only give you credit in one. And if we look, like, because you go to UIUC, I assume because those course numbers are the same as courses that I've seen. And I've also seen credit is not given to both courses like a billion times in the course registrar. So if we look at CS 173, credit is not given for both CS 173 and Math 213. Yeah, so if you take Math 213, then you shouldn't have to take CS 173. I mean, some classes, let's see, like 225 requires 173. Oh yeah, see, one of CS 173 or Math 213. So yeah, you should not have any problems taking Math 213 and not taking, yeah, because all the upper level classes are just going to say CS 225, and you can say you can take CS 225 with Math 213. So yeah, you don't need, or you're transferring from or to UIUC for, yeah, you shouldn't need to take 173 if you've taken 213. I actually think they won't let you register for 173 since you've taken 213. I think they're equivalent. Let's look up what Math 213 is. I've taken 173, so we can see if like they're the same class or not. Basic structures, algorithms, induction, counting. Yeah, they're the exact same class. Yeah, it's the exact same. This is the exact same class. Yeah. So you don't have to take discrete math 173. What would your advice? A white man get a flow as fire as yours? Grow your hair, bro. Get some nasty flow. I don't know if my car is even here though, because my brother had it. Oh no, my car is definitely here. My keys are right here. Are you from Illinois? What community college do you go to? I have well, actually I have to leave. I don't really have that many minutes. $90 to Pearson. Oh yeah. Yeah. Are you trying to transfer into CS at UIUC? Dude, these cats just get kind of ridiculous. Alright, whatever. I'm gonna end stream. Yeah. Oh yeah, you're trying to transfer into CS. Well, good luck to you, bro. Sounds like if you've taken Math 213 at community college, I mean, you should be fine, cause then you're at the same level as I am currently, I would assume. So you should be completely fine to get in. I mean, most incoming students. Oh, you got accepted as CS plus Math. Oh, okay. Okay, you got accepted. That's good. Oh, CS plus Math. Damn, bro. You take hella math classes. I actually, out of the CS plus majors, the only ones that I would like consider doing are CS plus bioengineering, CS plus physics, and then CS plus math. Those would be the only 3 that I would be interested in. So CS plus math is pretty cool. When I was, for my year, I can't even do CS plus bioengineering or CS plus physics because it's for the incoming class, but CS plus math was pretty interesting because that was actually like I was able to go into that one, and I was contemplating whether I would do it or not. I decided not to, but I could have. Yeah. But I'm dipping. Alright. Told you guys it'd be a short stream. I'm ending stream here. I might stream later when I do work later because I'm for sure gonna do more physics later, but I'm not doing it right now. I have too much stuff to do. Alright. This cat is on my keyboard as always. Can't end stream because this cat is pressing buttons on my keyboard.